over the long distances. Now, we need to know the mathematical equations, the instantaneous equations. Now, those instantaneous equations, as we remember from the single phase supply, that the instantaneous voltage means the voltage at a particular instant on a sinusoidal waveform is equals to the peak voltage times sine of theta. If it is an angular, that will be instantaneous voltage is equals to the peak voltage sine of 2 pi ft. F frequency, T time period. Sorry, T is not time period. T is the time at which you want to calculate the instantaneous voltage. So that was the time when we did in single phase system. But in three phase systems, we can apply the same equations. As you can see, that this is the stator and this is the rotor. When the rotor rotates, it will induce three separate voltages when it completes one cycle of rotation. So you get the three voltages when the rotor completes its first or rotation, 360 degrees. And we can represent this mathematically. That will be the instantaneous voltage EA, means the coil A, or coil U, is entirely up to you, is equals to the peak voltage or Emax, maximum voltage. It's a different representation, but they are all the same thing. The coil A would have the peak voltage sine of theta degree. This is considered as a reference angle, which means that the coil A has a 0 degree angle. So you don't need to write here 0 degree angle in the first equation. Coil B starts, that's your yellow coil, coil B, has minus 120 degrees difference, angle difference. So you can say that peak voltage or Emax is equals times the sine of theta, whatever the angle, minus 120 degree. So for example, if the angle here at particular instant is 0 degree, that theta would be 0 degree, that you are interested to calculate the instantaneous voltage. We used this equation in the past to calculate the instantaneous voltages in our first few weeks. This theta represents the angle at which you are interested to calculate the instant voltage at particular instant. So if you want to calculate that particular instant, let's suppose 0 degree, then here the theta would be 0 degree minus 120 degree. And this will give you the instantaneous voltage in coil B. Make sure you do multiply with the peak voltage. So peak voltage will always be constant. Similarly, in coil C, you will have the maximum peak voltage times sine of theta plus 120 degree. All the same thing, minus 120 plus 120. So these are the mathematical equations in degrees. We are going to use these equations hopefully in degrees. But in case if you are interested in angular or radians, then your equations can be represented as a Emax sine of omega t. Now here omega is 2 pi f, angular velocity, and this t is the time at which you are interested to calculate the instant voltage. So t is a small, it's not a time period, it's a small. And again, omega t minus 2 pi by 3 and plus 2 pi by 3, which is the same in degrees, that would be minus 120 degree and plus 120 degree respectively. Now this was all about how the three-phase voltage is being generated, where it comes from. Well, it comes from the generator, and we can represent this with three separate instantaneous voltage equations, and each voltage would have electrical 120 degree with respect to each other, because the windings placed onto the stator are 120 degree with respect to each other. We can represent this on phasor diagram, and you do remember the phasor diagram. We can represent the voltages and the currents by using a particular scale. Drawing the lines is the same thing here, same thing, except you have to consider the angles for the three separate voltages. So for example, you have the first voltage angle at 0 degree, which is considered as a reference. Why? Because the waveform starts at 0. It is our initial assumption. The second voltage EB has minus 120 degrees, so you start from the negative axis. And the third voltage or induced EMF would be having a plus 120 degree, that is your EC. So this is the phasor diagram that represents the three induced voltages or three instantaneous voltages. Now phasor diagram plays a significant part here. That's why we've been trying to focus on drawing the phasor diagram on organ diagrams, complex representations. It was all about to make sure when we do study the three-phase systems, we should know what the phasor diagram is, how we can draw phasor diagram more accurately. But make sure all three voltages must be 120 degree with respect to each other. That's the most important thing to notice. Again, it's the same thing which I have drawn before. So you have three separate voltages, and this is the omega that represents the direction of the rotation, and these are the instantaneous voltage equations. Again, this is the repetition. Now you might be wondering what this AN, BN, CN means. This is the most important part of the lecture. This is a quick revision slide how we can convert polar into rectangular form, rectangular into polar form. I shouldn't be doing it, but just to make sure that we do know how to use a calculator to convert rectangular form to polar form and vice versa, because in this lecture, in this learning outcome, we will be using these complex rotations quite a lot. So once we generate a three-phase power from the synchronous generator, for example, we need to supply that power to the load through the transmission lines. Now this is the diagram that I try to show, that how we transmit power from the central power station where we have the generator, then you have a transmission lines, then you have a distribution systems. And all of these systems, what you see, these two circles means transformers. So once we generate the three-phase voltages from the synchronous generator, we need to step up the voltage using a transformer. And you know why we need to step up the voltage, because if I increase the voltage, I reduce the current. If I reduce the current, I reduce the size of the conductors and the power losses. That's why we here transformers play a significant part. At the time when the power needs to be consumed at the distribution level, it needs to be stepped down. But in order for us to generate three-phase voltages and then transmit that three-phase voltages through transformer, we need a particular system, and that system is called star and delta system. Now, star and delta systems, they are quite traditional, but nowadays with the use of power electronics drives, it is possible to automate the process, but it does have a power losses. So star and delta is the fundamentals in electrical engineering, where we still apply these concepts. But of course, you should be thinking, what is star, what is delta, why we need to have two systems? Well, I just want to simplify. If you have three separate conductors that has three generated voltages, those three generated voltages need to have a particular system to transmit. So one is called star and another is called delta. I said in the previous slide, here AN, BN and CN, very important parameters. Now these AN, BN and CN induced voltages are relevant to the star connection. So we are going to look at the first system in three-phase supply called star connection. The star connection means it resembles the structure of a star. So you have three separate conductors connected. One side is connected together at one particular point, and another sides are connected to the voltages, but there will be one more connection called neutral. So let's suppose what you're looking at right now, the diagram, you have three separate voltages coming out from the synchronous generator. Now, three voltages must be consumed to a load like a medical equipment that requires three-phase supply. So let's suppose this is called the impedance load. You have three voltages coming into the load, and this is the star connected system because the loads and the supply must be connected to a particular system. So we call it star because one point of the load is connected together, another points are connected to